Momentum is a concept that permeates our understanding of motion, and it's particularly fascinating when we consider how it applies in the world of sports, especially in rugby. Picture this: a large rugby player, muscles rippling, barreling down the field at full speed. Now, contrast that with a skinny player, casually strolling along the sidelines. The difference in their momentum is not just a matter of how fast they're moving. It's a product of their mass and their velocity, encapsulated in the equation momentum equals mass x velocity. Let's break this down. Momentum in physics is the quantity of motion an object possesses. It's a vector quantity, meaning it has both magnitude and direction. The larger the mass of an object and the faster it moves, the greater its momentum. So when we consider our large rugby player, let's say he weighs around 120 kilograms. If he's sprinting down the pitch at a speed of 10 meters per second, we can calculate his momentum. Using our formula, we multiply his mass by his velocity, 120 kilograms, times 10 mesobases equals 1200 kilograms. That's a significant amount of momentum. Now let's take our skinny player. Perhaps he weighs in at a mere 60 kilograms, and instead of sprinting, he's walking at a leisurely pace of 1 meter per second. If we apply the same formula to him, we find his momentum is 60 kgs times 1 millimoles, which equals 60 kilograms. The disparity is staggering. The large player's momentum is 20 times greater than that of the skinny player. This is why, in a collision, the larger player can easily knock the smaller one over. He has more momentum propelling him forward. But why is this important? Well, momentum is conserved in a closed system, which leads us to another crucial principle. Momentum before equals momentum after. This means that in any collision, the total momentum of the system before the impact will equal the total momentum after the impact, provided no external forces act on it. Let's illustrate this with our rugby players again. When the large player collides with the skinny player, the momentum they each possess will interact. If the big player with his 1200 kilograms of momentum collides with the skinny player who has 60 kilograms, the outcome of that collision will depend on how they interact. If the skinny player is stationary, his momentum is 0, and the total momentum before the collision is simply the large player's momentum. After the collision, assuming an elastic collision where both players bounce off each other, the momentum is redistributed. The large player may lose some speed, and the skinny player will gain speed as a result of the impact. This principle is not just theoretical. It has real-world implications. In sports, understanding momentum can help players anticipate the outcomes of collisions and strategize their movements. Coaches analyze these dynamics to develop training regimes that enhance players' mass and speed, thereby maximizing their momentum. Players who can harness their momentum effectively can tackle opponents, break through defenses, and score tries. In summary, momentum is a vital concept that helps us understand the physics of motion, particularly in dynamic sports like rugby. The equation momentum equals mass x velocity succinctly captures how mass and speed contribute to the momentum of an object. Moreover, the principle of conservation of momentum illustrates how momentum before an event will equal momentum after, allowing us to predict the outcomes of collisions and interactions. So, the next time you watch a rugby match, remember that the clash between players is not merely a physical encounter. It's a dance of momentum, a beautiful interplay of mass and velocity that can determine the outcome of the game. Understanding these principles not only enriches our appreciation of the sport, but also deepens our grasp of the fundamental laws of physics that govern all motion.